All right, so today we're going to pull back the curtain on one of the coolest, most powerful ways we have to understand our incredibly complex world. It's called Discrete Event Simulation, and it's basically a clever trick that helps us see the future of everything from your local coffee shop all the way up to the entire internet. I mean, think about it. Our world is just built on these massive interconnected systems. So how do you predict a bottleneck in a supply chain? Or figure out how to manage city traffic? Or even just stop a website from crashing when it gets super popular? These are huge problems, and just, guessing is definitely not going to cut it. And it can be something you see every day, right? Like a coffee shop. How many people should be working behind the counter during that morning rush? You want to keep the line moving, but you also don't want to be paying extra staff to just stand around. There's a sweet spot, but how do you find it?
Or you could be dealing with something on a completely different scale, like a massive car factory. Making just one tiny change to one part of that assembly line could have these huge ripple effects that might save or cost millions of dollars. You absolutely can't just guess with stakes that high.
Well, the answer to all of this is simulation. The idea is you build what's basically a digital twin, a virtual copy of your real-world system. And this lets you play around, you can test out new ideas, you can ask all those what-if questions, and you can do it all safely and cheaply, without messing up the actual real thing. But okay, how do you simulate time itself efficiently? This brings us to the absolute genius at the heart of Discrete Event Simulation, or DES for short. It's got this one brilliant trick up its sleeve that changes everything.
See, you could try to simulate every single second or even every millisecond of a day. But just think about all the wasted computing power. For most of that time, literally nothing important is happening. DES is way smarter. It just ignores all the boring, empty waiting time and jumps directly from one important moment to the next.
And this brings us to the most important piece of the puzzle, the event. What's an event? Well, it's any single moment in time that actually changes something in the system. A customer walking in the door? That's an event. A machine finishing its job? That's an event. A tiny packet of data arriving at a router? Yep, that's an event too. These are the only moments that the simulation actually cares about. Here's a perfect way to think about it. Imagine you're a railway station master. You're not sitting there watching the clock tick by. 10:01, 10:02, 10:03, that's useless, right? You only care about the moment a train arrives or the moment a train leaves. Everything else in between is just waiting. DES works exactly like that station master. And this timeline shows that idea perfectly. Look, the simulation clock doesn't tick along smoothly. Nope. It starts at time 0 for event A, and then, bam, it instantly jumps all the way to 1.2 seconds for event B. It just skips everything in between. Then it jumps again to 4.7 seconds for the next event, and so on. That is the time jumping trick in action. Okay, that sounds cool, but how does a computer actually pull this off? Let's pop the hood and take a look at the engine that actually runs one of these simulations. It really all boils down to just 3 main parts. First, you've got an event queue. You can just think of this as a to-do list of everything that's going to happen in the future, all sorted neatly by time. Then you have the simulation clock, which just keeps track of our virtual time. And finally, you have the scheduler, which is like the engine that runs the whole show. And the process itself is this beautiful, simple loop. The scheduler just grabs the very next event off the top of that to-do list. Then it jumps the clock forward to that event's time. It runs the logic for that event. So maybe a new customer gets added to the coffee shop line. Now that action itself might create new events in the future, like this customer's coffee will be ready in 3 minutes. So that new event gets added back into the sorted list, and then it just repeats over and over again. Now, this is not just some neat little academic idea. This time-jumping trick is actually the backbone of how we design and analyze some of the most critical systems that we all rely on every single day. And the impact is just massive. I mean, think about the internet. How do you think engineers test out brand new ideas for how the internet should work without, breaking the whole thing? They use network simulators. And as this quote makes clear, every single one of the modern simulators that built our digital world, they're all powered by a DES engine. It is that fundamental. So let's jump back to our coffee shop. Over on the left, you can see a simulation with just one barista. And yeah, that's a long, unhappy line of customers. But on the right, we run the exact same simulation, but this time with a second barista. And look at that, the queue is way shorter. By comparing the results of these 2 virtual days,
A manager can make a really smart business decision without ever having to risk hiring someone new.
And its reach is just incredible. It's used everywhere. For optimizing factory floors and complex supply chains, for designing the scheduler inside your computer's operating system, it's used in high-stakes financial modeling, for figuring out how to manage patient flow in hospitals to cut down on wait times, and even for managing entire transportation networks. So, let's bring this all together. Why does this all matter? Why has this one specific method for simulation become so important across so many different fields? It really all comes back to that one single elegant idea. The secret sauce, the magic ingredient, is just skipping the time where nothing is happening. By focusing only on the events that actually matter, you unlock this incredible efficiency.
This makes it super efficient. You're not burning through computer cycles simulating nothing. And because it's so efficient, it's also incredibly scalable. You can model massive, complex systems like an entire global communications network. But most importantly, it gives us real insight. It lets us test out all our what-if ideas safely, cheaply, and ultimately lets us build better, smarter, and more efficient systems for all of us.
So you see, this simple time-jumping trick isn't just a clever bit of code. It's a powerful toolkit for understanding and improving just about any system you can possibly imagine. It lets us peek into the future, test our wildest ideas, and engineer a better world. So the only real question left is, now that you know how to model almost anything, what problem are you going to solve first?